Welcome back to the Deep Dive. Today, we are charting what might be the biggest, most crucial shift happening at the bleeding edge of AI research.
Hmm.
For the last few years, the whole narrative has been dominated by this quest for the biggest, most massive monolithic model, the one system that does everything.
The bigger the better, right?
Exactly. But today, we are diving deep into a fundamental move away from that, toward these highly specialized compound architectures.
That's right. We've been handed a stack of really foundational research dissecting one of the prime examples of this shift.
Yeah.
A system they're calling ToolOrchestra.
And our mission for you today is purely academic, purely engineering focused.
Yeah, we're going to reverse engineer its core decision-making strategy.
Yeah.
We're drilling down into the economic drivers and, crucially, the specific mathematical foundation, the control theory, that they use to train its central brain.
The decision maker.
The decision maker, this 8 billion parameter router.
And this isn't just some, incremental improvement. This is a foundational change in how AI actually captures economic value.
It is.
The goal is no longer just to build this single smartest model. The goal is to train a system that is the best possible manager of a huge array of specialized resources.
And the documents we reviewed, they break down the entire theory layer across 4 major engineering pillars. These are the things that have to work for this architecture to succeed.
So that'll structure our deep dive today.
Exactly. First, the architectural thesis and the economic why. Second, what they call the calibration paradox, which is this fundamental cognitive failure of the big models.
Why they can't do this on their own.
Right. Third, the very specialized reinforcement learning formulation needed to teach strategy. And finally, the really, really tricky problem of multi-objective reward design, which, that basically defines the system's whole personality.
Okay, so if we need one core concept to kind of anchor this entire deep dive, what is it?
It's one word: arbitrage.
Arbitrage.
Orchestration is the new frontier, and it's driven by arbitrage. We are talking about capturing economic value by solving a complex, difficult task, maybe a PhD-level physics problem for, say, half a cent.
Instead of the 5 cents it would cost to just ask a huge frontier model like a GPT-5 to brute force it?
Precisely. The breakthrough isn't in creating new knowledge, it's in achieving radical efficiency.
Okay, so let's start at the beginning then, the blueprint. This router worker architecture is described as a specialized distributed system design. The key, like you said, is decoupling. What does that architecture look like in practice? Why is that separation so critical?
In practice, it's a very hard separation of duties. It actually mirrors a lot of best practices from systems engineering.
Okay.
They separate the control plane, which is the 8B router model that has all the routing logic, all the decision-making, from the data plane.
And the data plane is where the actual work gets done.
That's where the work gets done. It's the execution environment. It's where the workers live. These are the tools that do things like run code, search the web, or even, make a call to another larger model.
The analogy that's often used is the conductor and the orchestra, right?
Yeah.
Conductor, the router, doesn't play the violin,
Right.
but it coordinates the entire performance.
Precisely. And the central, I would say almost radical claim that ToolOrchestra is making is that routing is a distinct, specialized capability from generation.
A completely separate skill.
A completely separate skill.
Mm-hmm.
And they argue that using one massive set of weights to do both of those jobs is just cripplingly inefficient.
I really want to dig into that inefficiency because it feels like that's the economic foundation for this whole system.
It is.
When we look at a standard monolithic LLM, the same weights are being used for 2 profoundly different cognitive tasks.
Yeah, think about it this way. The training objective for a massive model, its whole reason for being, is to maximize the probability of the next token based on its training data.
So it's a prediction engine?
It's a prediction engine. And that process uses a huge amount of compute, engaging billions of parameters to generate a high-entropy, imaginative, creative output, like a poem or a story. That's task number 1.
Okay, the creative writer.
Exactly. But then, a moment later, you ask that same model to do a task that requires ultra-low entropy, a purely binary decision.
Yeah.
Like, should I use the Python interpreter to calculate the square root, yes or no?
And you're using that whole massive creative engine?
The entire multi-billion-dollar pre-training investment. You're using that imaginative engine to decide whether to, as you once said, switch on the headlights. It is so mathematically and economically wasteful.
The system is designed for one thing, generation, and we're forcing this other task, routing, into that same framework.
We are. And ToolOrchestra's solution is just to dedicate this 8 billion parameter orchestrator, this writer, solely to managing that problem-solving state machine. Its only job is to be the best possible manager, not the best generator.
But, 8 billion parameters still sounds huge for just a manager. Why not a much smaller model? Why not a 1B model?
Yeah, it's a great question, and it's something the engineers definitely had to figure out. Why not a 1B router, right?
Yeah.
The research seems to suggest that the 8B size is the minimum threshold required to encode the complexity of strategy needed for, robust generalization.
Strategy isn't simple.
Strategy is not simple at all. It involves assessing the ambiguity in a user's prompt, predicting the latency of different API calls you might make, estimating the difficulty of the computation required. It needs a vast parameter space to learn that subtle strategic map of the world.
So if the router were too small, it might learn a few simple tricks.
It would learn to route correctly for simple tasks that it saw in training, but it would completely fail to generalize when you give it a novel multi-step problem it's never seen before.
Yeah.
It would just break.
Okay, so 8B is the minimum viable product for a sophisticated strategist. And this brings us right back to the core economic driver, that arbitrage.
Precisely. This system is not designed for, anthropomorphic reasoning or consciousness. It's an optimization engine.
Pure and simple.
It's training a very specific policy to optimize a global cost-reward function across a vast, heterogeneous network of tools.
And these workers, these tools, they're not all the same.
Not at all. They are intentionally diverse. You've got a free, super-fast search index. You've got a cheap, reliable code interpreter, maybe a specialized high-accuracy classification model for certain tasks. And then you have the big one.
The most expensive tool in the box.
The single most expensive tool, the Frontier LLM, your GPT-4.
So the router's genius lies in figuring out the optimal mix, the cheapest, fastest, most accurate combination of these workers to solve any given problem.
It's resource management taken to an extreme.
And the performance results are what make this so compelling.
They're dramatic. When this decoupled architecture is trained correctly, which we'll get into, this 8B parameter, router shows superior performance on benchmarks compared to a much larger monolithic model trying the same thing, because it learns to delegate. It can solve PhD-level physics problems, which it has zero native knowledge of, simply by knowing that that calculation needs to be farmed out to the specialized code worker.
The intelligence is knowing who to ask.
Yep.
And that knowledge is worth millions in saved computation.
It is.
So that structural overview leads us perfectly into these 4 pillars that ToolOrchestra needed to solve, which will guide our deep dive.
Right. We mentioned control theory and scalarization, but it's important to acknowledge the others because they're inseparable.
Go ahead.
So, 1, control theory using reinforcement learning. How do we train the actual strategy? 2, scalarization. How do we unify conflicting goals like speed, accuracy, and money into a single objective function?
Okay.
3 is the supply chain. They call it tool scale.
Yeah.
How do you generate the massive, diverse, high-quality training data you need to teach these strategic decisions? That's the fuel for the engine.
And the last one.
The last one is production reality. How do you make sure this fragile routing logic generalizes and stays robust when the real-world mix of user tasks starts to shift over time?
All right. We'll dedicate the rest of our time to dissecting the math and the engineering behind these pillars. So let's start with that immediate technical roadblock. Okay, let's unpack this core cognitive failure. Why can't we just use the vast intelligence of a 175 billion parameter model to route its own tasks? Why do the engineers need to design a separate, expensive 8B router instead of just prompting the big model harder?
It really comes down to what that big model is fundamentally optimized for. The short answer is the calibration failure.
The calibration failure.
Yeah. As we said, LLMs maximize the likelihood of generating the next token that matches their training corpus. They're not optimized to minimize computational cost, and critically, they are not optimized to admit ignorance.
Or uncertainty.
Or uncertainty in a robust way.
That sounds like a profound misallocation of intelligence. The model is just too confident in its own statistically derived reality.
Exactly. When you ask it, what is the square root of 4913.08? The standard LLM feels, from its training objective, immense pressure to produce the next logical token.
To give an answer.
It starts generating one, relying solely on the patterns encoded in its internal weights. And if the precise answer isn't statistically available or easily recalled, it will smoothly, confidently, and often mathematically incorrectly just hallucinate the answer.
So the router's whole job is to interrupt that sequence. It has to insert a strategic decision node.
Right. It has to ask,
Uh,
is the precision required for this answer high enough that I must pay the cost to borrow external compute, or can I just rely on my internal, cheap, but potentially imprecise knowledge?
and that decision requires a totally different kind of intelligence.
A different kind.
Yeah.
One that's calibrated to real-world precision requirements
Hmm.
and, just as importantly, real-world costs. And despite what, many prompt engineers hoped for in the early days.
You can't just prompt our way out of this.
You can't. I imagine the product team initially tried that. They must have attempted simple instructions like, you are an expert. Only answer if you are 99% confident. Otherwise, call the search tool.
Right. So why did that prompting harder approach fail so badly that it necessitated this whole RL framework?
It failed because of two deep structural biases that are just baked into the model's core training. We saw these play out over and over again in the early attempts at tool use.
What are they?
They call them self-enhancement bias and other enhancement bias.
Let's start with self-enhancement bias. That sounds like algorithmic arrogance.
It is, in effect. LLMs tend to overtrust their own internal parametric knowledge base. I mean, a modern frontier model has ingested most of the human-generated digital text.
So it's seen everything.
Its vast weight matrices contain statistical patterns for almost everything, obscure math constants, historical facts, even patterns that relate to dynamic info, like current stock tickers. The model feels equipped to answer these questions internally.
Because the patterns are there.
The patterns are there, even if the encoded information is outdated or imprecise or just a statistical guess.
So if I ask it a niche historical question that requires a specific validated date, the model thinks it has that date encoded and will just refuse to call the expensive, slow external database tool, even if the date it spits out is off by 2 decades.
Precisely. It's like the incredibly smart but cocky student who thinks they don't need to double-check their notes. They rely on memory and statistical probability, which leads to high confidence but potentially very low precision. This bias just destroys the system's ability to route correctly when accuracy is critical.
Okay, but then if we try to correct for that, let's say by adding an aggressive instruction, you must verify all facts using the search API, we immediately run into the opposite problem.
You crash head-on into other enhancement bias.
And what's that?
That's the bias that kills the economic thesis immediately. The model becomes overly subservient to the prompt. It starts wasting resources by calling external APIs for trivial, zero-risk, high-confidence queries.
Why would you pay for a search query to confirm who is the president of the United States?
Or what is 2 plus 2? The cost arbitrage just vanishes because the system is constantly burning micropennies on totally unnecessary API calls.
Yeah.
It turns from a smart manager into a trigger-happy spender.
This systemic instability, then, the model swinging between aggressive self-reliance and wasteful over-reliance, proves the core conclusion.
Yes, the model's internal confidence signal, the probability it assigns to the next token, the 2 token, is simply too noisy and unreliable to map to a simple heuristic. You can't just write a rule that says, if token is less than 0.95, call the tool. It just doesn't work.
So we have to train a strategy, not just a set of rules. This is where the whole structural transformation happens, moving away from simple token prediction into a sequential decision process.
This is where it gets absolutely critical for you to understand the shift. Orchestration transforms the entire problem space. It's no longer about generating a stream of text.
What is it about?
It's about generating a trajectory through a state space, a sequential decision process.
Let's visualize that trajectory. It's a chain of events, right? The output of one action feeds into the next decision.
Exactly. You start at the initial state, which
Yeah.
is the user's query. The writer's first output is an action. Maybe call the specialized math code interpreter.
Okay.
That tool's output is then fed back into the system, resulting in a new state. This was the one. Maybe that's a successful computation result, or maybe it's an error message.
And the router sees that new state.
It sees young dollars, and then it chooses the next action, $8 one. Maybe that's reformat the calculation and retry. Or maybe it's generate the final answer, and this continues until you reach the terminal state.
This sounds like a perfect setup for traditional supervised fine-tuning, or SFT, If we have millions of examples of successful trajectories, why can't we just SFT the 8B router to learn that sequence?
SFT is critically insufficient for training strategy. It's a great tool, but it's basically behavior cloning.
Behavior cloning.
It excels at teaching syntax how to format a tool call in a perfect JSON block, for instance.
Yeah.
But SFT works by minimizing the difference between the model's output and the reference data.
Okay.
So if your high-quality training data, the stuff from the tool scale pipeline, only shows one successful path, say using the Google Search API for a specific query, the model gets severely penalized if it chooses an alternative.
Even if the alternative works.
Even if an alternative like Wolfram Alpha or a specialized database is cheaper or faster or better. SFT punishes any deviation from the single correct path that was shown.
So SFT forces the model to memorize specific paths, not learn a generalized, flexible strategy that can adapt to new costs or new tools.
That's the core of the problem. You face the classic bias-variance trade-off. SFT keeps the variance low. It sticks very close to the known path, but it introduces this massive bias because the model can't generalize or discover solutions that weren't explicitly shown in the training data.
And we need a system that can explore.
We need a system that has the freedom to explore the tool space, to reduce that bias by finding novel, more efficient trajectories. And it still has to converge on the optimal, most cost-effective solution, which manages the variance.
So what's the solution?
The only established field designed for this kind of exploration and strategic decision-making in a sequential environment is reinforcement learning.
Right. And the big breakthrough here is realizing the 8B model doesn't need to learn how to solve PhD physics. It just needs to learn a much simpler function.
A much simpler function.
Yes.
That it does not know the answer and who to delegate it to. That's it.
So RL is the required framework to teach this strategic delegation. But applying RL to a system that lives inside a neural network, yet relies on external APIs, it introduces this fundamental hurdle that just breaks standard training methods.
It does.
Let's talk about the physics of backpropagation and what the documents call the broken chain of computation.
This is one of the most critical technical challenges the ToolOrchestra team had to solve. Standard neural networks, they train using gradient descent. And to update the network's weights, you have to calculate the gradient of your final loss function with respect to every single parameter in the network. This requires the entire operation to be differentiable.
Meaning a gradient, a signal, has to flow backwards through everything.
A signal, a measure of how much a small change in an input affects the output, must flow backwards through every single layer, every matrix multiplication. The whole chain has to be connected.
And if the model is just generating text internally, that computational chain is solid. It's all just vectors and matrices flowing from one layer to the next.
Exactly. But the moment the 8B router generates the tokens for a tool call, say a Python code block requesting external data, that sequence of tokens gets passed to the outside world.
To the worker.
To the worker. The external Python interpreter executes the code. This physical execution, this interaction with the outside world, is mathematically non-differentiable.
You can't calculate the gradient of request.get an external URL with respect to the attention weights in layer 3 of the 8B model.
You just can't. The information chain is severed right at that API boundary. The model performs an action in the real world, and the gradient cannot flow back through that real-world action.
So what does this all mean for the engineers? How do they get around this?
It means we can't use the standard backpropagation techniques. The only feedback signal that links the action, the tool call to the result, the cost, the latency, the final correctness, is the ultimate reward earned by the entire sequence of decisions.
So you have to assign credit after the fact for the whole sequence.
Retrospectively across the entire trajectory.
Yeah.
Which brings us to the classic RL setup, the policy gradient solution.
Okay.
We have to treat the system as a classic Markov decision process. The tool call is the action dollar taken by our parameterized policy. That's our 8B router.
And it takes that action within an environment.
Within an environment, which is the heterogeneous network of workers. The core objective then becomes maximize the expected cumulative reward, represented as across all possible decision trajectories.
And the specific mathematical breakthrough that they use here is the reinforce algorithm, or the policy gradient theorem. I remember learning this concept years ago, and it's really elegant in its simplicity.
It is elegant, and it's absolutely crucial here. Since we can't differentiate through the non-differentiable environment, reinforce gives us a way to estimate the gradient of that policy objective.
And it doesn't rely on local token-by-token errors like backpropagation?
Not at all. It observes entire trajectories.
Hmm.
So if the model tried a novel sequence of actions, used a new combination of workers, and that whole sequence resulted in a high positive reward, say, it solved a complex problem accurately and for the lowest cost ever observed.
Then what happens?
Then the reinforce mechanism, through its mathematical formulation, allows the policy to increase the probability of all the individual actions that were taken along that successful trajectory.
It's retrospective credit assignment.
That's it. It learns from successful strategic sequences, not from local errors. This is how the 8B router learns that retry with corrected code is a valuable sequence, even though the first failed code execution generated a negative state.
Because the ultimate success justifies the intermediate failures.
Yes, and that makes the complexity of the 8B model suddenly justifiable. It's not just learning facts, it's learning this complex statistical map between an initial prompt, the current state, and the probability of taking action A versus action B, where A might be call tool and B might be generate answer.
Okay, so we've established that RL is necessary, and reinforce provides the math. But when it came time to actually select the specific RL algorithm, the ToolOrchestra team made a highly unusual choice: Group Relative Policy Optimization, or GRPO.
Yeah, that one's interesting.
Why skip the industry standard KPO, proximal policy optimization? I mean, that's the gold standard for stabilizing RL training, especially in language models. We see it in RLHF all the time.
This is a textbook case of engineering design being dictated by economic and hardware reality. The decision to use GRPO was a conscious, painful trade-off driven entirely by VRAM constraints.
The memory on the GPUs, so the PPO problem is memory size.
Exactly. PPO achieves its stability by training a separate critic model.
A second model.
A second model. And the critic's job is to estimate the value function, $5. This function predicts the expected future reward from any given state, and it acts as a learned baseline, a crucial point of reference that reduces the variance in your gradient updates. Is what makes training stable and fast.
But if the orchestrator itself is 8 billion parameters, that critic model also has to be pretty large to be effective, which basically doubles your memory load.
It does. The 8B router needs about 16 GB of VRAM just to hold its weights in BF16 precision. You add an 8B critic, you immediately jump the required model memory to 32 GB per GPU. Now, think about their hardware. Even if they are using state-of-the-art GPUs, say H100s with 80 GB of VRAM, doubling the model size forces them to drastically cut the available memory for their batch size.
And in RL, particularly when you're dealing with noisy real-world data, the batch size is king.
It's your number one countermeasure for noise. Small batch sizes in RL lead to high gradient variance. The estimated gradient just bounces all over the place.
Which is bad.
It's very bad. High variance means unstable, noisy, and potentially destructive training. It can cause the policy to completely forget what it learned earlier, which leads to divergence or mode collapse.
So the engineering choice became, do we sacrifice stability and use PPO with a tiny batch size, or do we sacrifice memory and use PPO but require twice the physical GPUs, or do we find a completely new method?
And they chose the third option, GRPO. It's the VRAM hack.
The VRAM hack, I like that.
GRPO systematically removes the need for that external critic model. It requires 0 additional parameters.
So how does it create a baseline?
Instead of comparing the reward of a specific trajectory to a learned baseline from a critic, it compares the reward of that trajectory to the group average reward calculated across the entire batch of trajectories you're currently processing.
Okay, let me make sure I and you at home grasp that distinction. If I run a single trajectory and I get a final reward of, say, plus 0.8, PPO would compare that plus 0.8 to a constantly refined theoretical estimate of what that state is worth from the critic.
Right.
But GRPO just compares that plus 0.8 to the actual average reward generated by the, say, 1,024 other trajectories in that same batch. Maybe the average was plus 0.6.
That's precisely right. If you got a plus 0.8 and the average was plus 0.6, you get a positive update signal. Your policy is reinforced.
And if the average was higher?
If you achieve plus 0.8 and the group average was plus 0.9, you actually get a slightly negative signal, even though you succeeded, because you were less efficient than the average.
That just sounds inherently noisier.
It is. It is fundamentally noisier. That is the accepted trade-off. However, because they're no longer spending VRAM on a critic model, they can allocate all of that saved memory to increasing the batch size significantly.
Just smooth out the noise.
To smooth out the noise. The internal documents confirm this was the explicit strategy. They used a cluster of 16 high-end GPUs specifically to achieve massive batch sizes, which counteracts the noise generated by using the group average as the baseline.
They traded parameter efficiency for training stability, paid for by sheer scale of hardware.
That's the trade. It's a fascinating constraint optimization problem.
But as we discussed earlier, anytime you introduce a new non-linguistic reward objective like be cheap, you invite the danger of reward hacking or mode collapse where the policy optimizes for the reward in some unintended way.
For sure.
How do they stop the 8B router from just outputting gibberish or devolving into a policy that only ever uses the cheapest tools no matter what the prompt is?
They install a crucial safety mechanism, which they call the KL divergence penalty. Think of it like a linguistic leash, or maybe a speed limiter on a race car.
I like that. A speed limiter that ensures the policy, can optimize for speed and efficiency, the new RL objective, but it can't violate the rules of the road. It can't stop being coherent.
Exactly. The total reward that's used for the gradient calculation is modified by subtracting this penalty. The formula is no total r stat beta plus theta chirum.
So what are those terms?
The term DQL naught measures the statistical distance, the difference in probability distribution between the newly RL trained policy, that's Pydetic, and the original reference policy, Pyrophate.
And Pyrophate is just the pre-trained non-RL model that already knows how to speak fluently and structure arguments logically.
Correct. So by penalizing any divergence from that reference policy, the system is forced to optimize for cost, accuracy, and latency within the boundaries of sensible human language.
It ensures that the model doesn't, for example, learn to just output 3 random words that happen to satisfy the regex for a successful search query, because that path maximizes the reward.
It has to remain grammatically coherent and logically sound while it's pursuing the efficiency objective. And that factor, beta, is a hyperparameter that controls the strength of the leash, how strictly the policy has to adhere to its linguistic groups.
That's a brilliant way to handle 2 conflicting demands. We want the model to aggressively explore new cost-saving strategies from the RL, but we need it to remain stable and communicate clearly, which is the KL penalty part. The technical challenge of training the policy is obviously immense, but the philosophical challenge of just defining what success looks like might be even harder.
That might be.
This is our 4th pillar, scalarization. We are dealing with inherently conflicting objectives. We want to maximize accuracy, but minimize latency and also minimize cost. The business goal is a vector of concerns, but RL demands a single scalar value, $2.
This is where we leave the pure math of neural networks, and we enter the world of corporate strategy. As the research notes point out, there's no single best orchestrator. There's only a Pareto frontier of trade-offs.
Explain that.
Well, you can build a very expensive, very fast, very accurate orchestrator, or you could build a very cheap, very slow, medium accuracy one, and everything in between. To use RL, we have to perform scalarization. You have to pick a specific desired point on that frontier and collapse all those concerns into one number that the gradient can follow.
So ToolOrchestra defined 3 main reward components to create the single scalarized objective. Let's start with the one that drives the core outcome.
That's the outcome reward.
Right.
This is usually the simplest. It's often just a binary signal, +1 for a correct final answer, 0 for failure.
But that has its own challenges.
It does. The big challenge here is the sparse reward problem. The model might take 5 different tool call steps, but it only gets that +1 reward at the very, very end. It forces the model to learn a long chain of causation, that the tool calls in step 1 and 2 were good ideas because they contributed to the successful outcome in step 5.
Okay, so that's the outcome. Then we have the crucial disciplinary component, the one that enforces the whole arbitrage thesis.
The efficiency reward. This is where all the cost control happens. It's structured as a negative penalty. The formula is basically re-efficiency cost plus sick normalized latency.
So the 8B router is essentially charged an internal tax for every token it generates and every second it makes the user wait.
It's an internal tax, yeah. It learns to internalize the cost of its own actions, viewing every single decision through the lens of efficiency.
And finally, they introduced a layer of dynamism on top of that, the preference alignment.
This allows the system to be adjustable without a full retraining. If a user is on a slow mobile network and explicitly says they prioritize low latency, the RatePro component can dynamically increase the weight, the rollout within that efficiency penalty.
So it shifts the target point on that Pareto frontier.
It does. The core policy is the same, but the internal exchange rate it uses to value time versus money changes based on the consumer's immediate demand.
Now we hit what feels like the biggest practical implementation challenge here, the scale mismatch problem. We're trying to sum 3 wildly different metrics: accuracy, which is between 0 and 1, latency, which could be 0.5 seconds to 10 seconds, and cost, which could be 0.0001 to 0.005 cents.
The raw numbers are all over the place.
If we just sum those raw numbers, the magnitude of the latency term would completely overwhelm the other two.
Completely. If you just sum them, the gradient update would be dominated by one thing, minimizing the seconds spent waiting. The model would learn one policy above all else: be fast.
And it would sacrifice cost and accuracy.
It would sacrifice them completely just to shave a tenth of a second off the response time. The entire multi-objective optimization just collapses into a single objective: low latency.
So how do they create a fair exchange rate between these things?
The solution is really ingenious. It's batch normalization, but applied specifically to the cost and latency terms.
How does that work?
Instead of using the raw dollar amount or the raw time in seconds, the system tracks the moving average, the mutter, and the standard deviation, the sigma of cost, and latency across the current training batch. It then normalizes these values to a standard normal distribution, where the mean is 0 and the standard deviation is 1, before the reward calculation begins.
Let's expand on that. It's like a central bank setting an explicit exchange rate.
That's a perfect analogy. Imagine a financial system where you can trade two currencies: time and money. Before normalization, time is traded in seconds. These are large numbers. And money is traded in fractions of pennies, tiny numbers. The exchange rate is wild and chaotic.
Right.
By normalizing both to be expressed in standard deviation units, the system forces mathematical parity. If the weights, costs, and lies are set equally, the model learns that one standard deviation of increased cost is perfectly equal to one standard deviation of increased latency. The RL optimizer then searches only for actions that respect this implicit normalized balance.
That seems like a required step for any multi-objective optimization in a business context, not just AI. But the documents mention a pretty significant limitation in the method they chose.
They do. They highlight that ToolOrchestra uses linear scalarization, a simple weighted sum. And this is chosen because it's computationally simple, it's fast to calculate, and it's stable during training. But linear scalarization has a known weakness in optimization theory. It cannot find optimal solutions in non-convex regions of the proto-frontier.
What does a non-convex region mean in the context of routing strategy?
Imagine the ideal solutions plotted on a graph of cost versus accuracy. If the true optimal solution set is shaped like a boomerang, a smooth curve with a sharp corner, the linear scalarization line will only touch the curve at certain points.
It'll miss the corner.
It will systematically miss that sharp corner, which might represent a novel, highly desirable trade-off, maybe extremely high accuracy achieved with only a small, sharp jump in cost. A linear sum just can't navigate corners or sharp shifts in the cost surface.
So they're essentially accepting that their current orchestrator will not find the most mathematically complete global optimum.
They're trading that possibility for faster, simpler development. It's a huge operational trade-off, accepting suboptimality in exchange for stability.
And this leads us directly back to the final crucial component: production reality and the risk of mode collapse.
The risk is that the model becomes a computational miser. If the reward function is successfully optimizing for low cost, the model will find the easiest path to that low cost.
Yes.
Stop using expensive tools entirely. It drives the cost term towards zero, but then the outcome reward also collapses to zero because the system can no longer solve complex, difficult problems. The router becomes cheap, fast, and completely useless.
So the solution can't be purely internal to the model. It has to be injected externally through the training data itself?
Precisely. This is the hidden dependency that connects the supply chain pillar, tool scale, to the production reality killer. The reward function only works as intended if the training set S, the task difficulty distribution, contains a sufficient number of problems that are mathematically impossible to solve cheaply.
The system has to be continuously exposed to problems that force it to justify the expense of the better tools.
Yes. Those hard tasks compel the orchestrator's hand. They force it to use the expensive GPT-4 worker or the specialized code interpreter, justifying the large negative efficiency penalty with a high positive outcome reward of +1.
And if the training data gets skewed?
If the training data becomes skewed towards easy, simple search lookups, the efficiency penalty dominates, and the learned policy quickly collapses into a cost-minimizing miser that refuses to manage complex tasks. The intelligence of the system in production is entirely dependent on the quality and the difficulty distribution of the data generated by that tool scale pipeline.
Which means that maintaining this compound system in production requires constant monitoring of the task distribution. If the real-world mix of user queries shifts too far toward the trivial, the policy will drift and start failing on the hard problems.
And that is the core fragility. The 8B router is not inherently a good manager. It is simply an optimization machine. It learns a policy that works for the specific tension between cost and reward defined by its training data. If that tension relaxes, the policy relaxes its performance standards.
This has been an incredibly detailed look into the economic and mathematical decisions driving these new compound AI architectures. It's pretty clear this is where the industry is heading. Let's quickly review the major surprising takeaways for you.
I think first and foremost is the economic thesis. Arbitrage. The primary goal is not generating better language, it's training an efficient manager, the 8B router, that minimizes operational cost by strategically delegating to the cheapest available worker.
Right. Second, the core failure of monolithic systems. The calibration paradox, which is driven by that self-enhancement bias. LLMs maximize token likelihood, not cost minimization, and that forces the shift from simple prompting to complex reinforcement learning and sequential decision-making.
Third, that huge engineering trade-off that was driven by hardware constraints.
Okay.
The GRPO VRAM hack. ToolOrchestra sacrificed the stability of a dedicated credit model just to save memory.
So they could use that memory for massive batch sizes needed to offset the resulting noise.
Exactly. They traded parameter efficiency for training volume.
And fourth, the successful management of that scale mismatch problem through batch normalization. By forcing time and money to be expressed in these normalized standard deviation units, they create a stable internal exchange rate.
Which enables the policy to balance accuracy, cost, and latency effectively.
Yeah.
The entire system works because the designers successfully turned a complex, multidimensional business objective into a single scalar number the gradient could follow, always constrained by that KL divergence penalty to make sure the policy remains grammatically and logically coherent.
Which brings us to our final provocative thought for you. Based on that hidden dependency we just discussed, we've established that the system's strategic intelligence, its willingness to pay for complexity, is entirely dependent on the task difficulty distribution used during its training.
Right. The policy only learns to be a successful problem solver because the training data forces it into these difficult, expensive decisions.
So consider this. How fragile is this strategically brilliant system when you deploy it in a highly dynamic production environment? If, over time, the real-world ratio of trivial tasks to impossible tasks shifts dramatically, maybe your user base starts asking mostly simple definitions, reducing the pressure to perform complex calculations.
What happens then?
Will the meticulously balanced optimization policy quickly collapse back into a cost-minimizing miser mode, forgetting how to handle the hard problems when they eventually do arrive?
The intelligence is defined by the tension it navigates. If the tension disappears, does the intelligence disappear too?
That dependency suggests that while these compound AI systems offer massive efficiency gains, they introduce an entirely new dimension of operational fragility that demands constant surveillance, something to mull over as orchestration becomes the industry standard. Thank you for joining us for this deep dive.